This is one of the driest places on Earth. Sometimes it feels like being on the Moon or Mars.
During the day is a fantastic place, but during the night is absolutely astonishing.
Hi everybody, welcome to this last event of the journey through the extreme universe. I hope you have enjoyed the series and learned about the exciting science that CTAO is going to perform. But it's not over yet. Today we are going to talk about the multi-wavelength and multi-messenger astronomy. What this means, what does this mean? Why everybody is talking about that? To answer these questions, we have today here with us an expert in the field, Professor Sera Markoff. But before introducing her, let me remind you, as usual, that if you have any comments, questions, you can leave them already during the webinar on the CTAO Facebook and YouTube channel. At the end, we always have this question and answer session, and Sera will try to answer all those questions, all those stuff. So without any further, let me invite Sera to join me here on the screen. Hi, Sera, how are you?
Hi, Alba.
So thanks a lot for joining us today. Before starting, let me introduce you to the people that doesn't know you. So Sera Markoff is a full professor at the University of Amsterdam. She's a very well-known expert in astrophysics and astroparticle physics, focused particularly on accretion processes around black holes from both galactic and extragalactic sources. She serves as vice chair of the Science Council at the Event Horizon Telescope Project, and she's a member of the Cherenkov Telescope Array Consortium. Among other honors, she was named Fellow of the American Physical Society and received several awards for her participation and organization of the outreach and education programs, particularly focused on diversity. So again, thanks a lot for joining us, Sera, and whenever you want, the floor is yours.
Okay, great. Thank you so much, Alba. And thanks to everybody who I can't see or hear for joining. I hope you're out there somewhere and that you'll ask questions at the end. And also, if you have more questions that we don't get to, feel free to ask me on Twitter. I'm always happy to answer questions. So before I get into explaining about what we mean by these, buzzwords of multi-wavelength and multi-messenger, I thought it might be interesting to start by talking about what does it mean when we say extreme universe in a series like this? Like, why is it extreme? What's extreme about it? And I think it's always nice to think a bit historically, because this is a really recent sort of modern question that we can ask. And what I mean by that is that for the majority of human history, up until the last maybe 100 or even less years, we've been really limited at what we can see based on what we can see with our eyes. So to the visible spectrum of light. And so that means that in the past, we were looking at stars, and these are star charts from various cultures, looking at constellations, making stories. And then even with the invention of the telescope in the 1600s, we were just enhancing still what we could see with our eyes. And for instance, these are sort of the chicken scratches of Galileo, who was looking at Jupiter and started to see some of the moons. But all of this is kind of the opposite of what we mean by extreme. So these objects like stars and planets, they're slowly evolving systems, and they manage to come into a kind of balance or an equilibrium. What that means is that the system has time to communicate across itself and come to a kind of agreement about what state it's in. And in physics, that agreement usually means settling on having a single temperature on average for the entire system. And so for non-extreme objects, we can characterize them as the light coming out basically at one particular frequency or a color. And there's this sort of one-to-one mapping to the system state. And this is something that I think we have quite a bit of intuition from being humans and being used to using our eyes. And for instance, so this is a picture of this is the Orion constellation. This is like a 1,000-year-old image here as well. And here you see Betelgeuse, a very bright star. And, when we look at like a fire, which is not exactly, it's not extreme, it's flickering as well, it's dynamic, but it's still in a sort of steady state. We have this idea or this intuition of a mapping of heat. We know that in general in a fire, also, if you have still have a gas stove. Some people do. I do. You get the blue heat, or the white heat is the hottest part of the fire. And as you move further away, it becomes sort of orangey red. And that's the same with stars. And so we came up with a system of stars to map the fact that their temperatures corresponded to their colors. And so Betelgeuse is a bigger, fluffier, and less hot star than some of these bluer stars as well. That whole thing breaks down when we get into the extreme universe. And that's because we're looking at different kinds of objects that are dynamically changing. They don't have time to talk to themselves across the system and come to this agreement. And they're much more powerful. And so, for instance, this is just a little bit of a cast of characters of some of the extreme universe that we see. And many of them involve, for instance, exotic kind of objects like supermassive black holes or stellar mass black holes or neutron stars or explosions. They tend to be extremely powerful. So stellar mass black hole or a neutron star, these are things that weigh more or less like a sun or a star, but they're actually having as much energy as millions of times of the sun coming out. So there's an incredible amount of power packed in, which makes these very much out of equilibrium. There's actually a lot of motion in these systems that can be near the speed of light. And so that breaks the ability to really settle into a like nice calm system. And you can see that in many of these systems, there's also these bipolar outflows that we call jets. And these turn out to be very good at exciting particles. So what happens is that all this energy, instead of just coming out in one nice temperature, suddenly comes out across the entire electromagnetic spectrum. And I'm going to say more what I mean by that. And then as well as coming out in light, we also have particles, different kinds of particles coming out that reach us on Earth. And we can also even have more recently gravitational waves. And I think what's amazing is to think about, you know, the fact, actually, before I say that, I just want to mention one other thing. These objects, because they're so powerful, actually have a huge impact on their surroundings. And so a lot of what we're trying to understand is not only how these objects work, often involving strong gravity effects, but also how they impact their environment. So just to give you a sense of some of the major outstanding questions, you know, we're just trying to understand, how is all of this stuff powered? Ultimately, we think that the fuel source in many cases is gravity, which is basically the mass of the object, you know, with its gravitational field manages to capture potential energy, capture mass, and then that potential energy gets channeled and converted into different kinds of forms. And what are these forms? And then there's two interrelated questions, which is, we see these very high energy particles on Earth. Which of these exotic objects and these extreme objects can be the sources? And that also relates to the question of the output, because if we want to know how they affect their environment, we also need to know what's inside of them. And the more particles they're putting out, the more sort of punch they can have on their environment in many ways. And then we'd like to track this back all the way to the beginning of the universe. So we're trying to also understand the evolution of these systems over cosmological time. Now, for the ones that involve strong gravity, we can start to probe the fundamental nature of space, and space-time, as we call these, are very linked together according to Einstein's theory of relativity. And we can even try to test theories of gravity. Also, when you pack all this energy into very small volumes, right before things become black holes and they stay as neutron stars, you really can see extreme matter, things that we can't probe on Earth. So altogether, these become basically cosmic laboratories for us. Now, we've got this really new window on the universe right now, which probably some of you have heard about. So just in the last 6 years, we've been able to see the ripples in space-time from merging black holes. Now we've seen them also merging neutron stars. And we've managed to take the first picture of the light, which is just outside the event horizon of a supermassive black hole with the Event Horizon Telescope collaboration. And so, you know, this is when we talk about multi-messenger, it means going away from just looking at the electromagnetic spectrum, which I'm going to say a little more about, and moving into particles, gravitational waves, and so on, and trying to get a complete picture of these extreme objects. And so we have to combine all of this information in order to understand them. So what I'm going to do in this talk is I'm going to be basically discussing these different messengers and kind of build one on top of the other. So I'm going to start with multi-wavelength. I use this acronym MWL just to shorten it. Sometimes you'll see that in some of the slides. And probably you're a bit familiar with this concept, but again, coming to this point of light mapping out something characteristic about the source, this is the electromagnetic spectrum. It spans over something like 20 orders of magnitude. This is a log scale. And something like the sun we said it's in this equilibrium, so most of the light is tuned, to come out where its temperature tells it to come out, which is in the visible range. And it's not a surprise that that's what our eyes can see. We evolved on a planet with the sun that's giving off all this visible light, so we evolved to be able to see this. But we can't see with our eyes a lot of these different wavelengths, so we have to build different kinds of facilities to measure them. And the sizes of the wavelengths and the energies, scale inversely with each other. So you can have hundreds of meters long for the radio waves, going all the way up to the ultra high energy gamma rays, where the wavelengths are actually probing, the size scales of subatomic, particle scales. And down here, this slide was made by our host, the Cherenkov telescope array. I'll come back to that. But here they talk about terrestrial sources that we made. But of course, we detect light from cosmic sources. And they put, because they wanted to emphasize that these cosmic extreme sources radiate very often in the high energy gamma rays. But unlike these non-extreme sources where there's a one-to-one mapping of the thermal state to one kind of light, they actually emit across the entire electromagnetic spectrum. They have huge amounts of power and they divide it up almost equally in many cases. And so that's why if we want to understand these things, we have to look at all these different wavelengths. It turns out to be really difficult to do because we can't just build one telescope to do this. So every telescope is designed to maybe pick out a piece of one of these wavelengths, and then we have to try to combine them. So I'll talk about that in a few minutes. But first, I thought what I would do is kind of give you an example of what we mean by multi-wavelength and what we can learn. And this is one of my favorite examples. It's a supermassive black hole. What you're seeing here is actually an optical image. So this is coming from the Hubble telescope. If you had really good vision and they shot you out into space, this is what you would see. And each one of these things is not a star. These are actually galaxies. And so it's a cluster of galaxies being held together by its own gravity. And this is the largest bound structure in the universe. And it's kind of like the birthplace of galaxies. They grow and they form together and they interact. And how do they interact? Well, there's a black hole in each of these galaxies, but we can't really see it so well with the optical because, as I was saying, it's spreading its energy out, but it's competing with the light from all the stars in the galaxy. But if we switch to another wavelength, we could see another aspect of the source. So I'm going to show you the same image, but now I'm going to add what we would see with a radio telescope. Now with a radio telescope, we can't see it with our eyes. So what we're going to do is we're going to make a fake color of this. So it's not really blue. I could make it, orange or pink or anything, but we like blue. So this is actually the jets that I was talking about, these huge structures being launched. There's a black hole buried deep within this galaxy. And these jets, this type of wavelength tells us something about magnetized material. So we know that this is strongly magnetized. We get information about it. We could track motions, and we know that it's being shot out from the black hole near the event horizon at almost the speed of light. And these things are billions of times bigger than the black holes that launch it. They extend way beyond the galaxy. And so you can see that they can start to affect other galaxies in this cluster. And if we want to understand how much energy is carried in, we could start to look at another frequency. So I'm going to show you now, I'm going to add X-ray to this, also in a fake color. So now it's a nice rosy pink. Now, this X-rays are tracing really hot gas. So gas that's about as hot as our solar corona, about 10 million degrees. And space is really cold, okay? And stars like to form when it's cold because then the gas can condense and they can basically start to burn hydrogen. So if you start dumping all this heat into this vast area, you get a sense of how much energy is involved, but also by all this, what we call feedback, the black hole and all the black holes together can start to alter each other's evolution and in fact stop the growth of galaxies because it'll stop the star formation. So this gives you an idea of how we can, start to learn a lot of things and put all these different pieces together. Now, we can measure all of this just by the observations, but when it comes to modeling, it's very difficult because all of this energy is being sourced. And I should mention that the energy being dumped in one episode of these jets, because this is also a sort of cyclic behavior, it can last something like 100 million years, 50 to 100 million years, can dump the equivalent energy of 100 billion supernova into the surroundings, just to give you some idea. So this is of course, we want to understand this. But we need to get down to the event horizon and really try to probe what's going on there. And that turns out to be quite difficult. And so for that reason, we decided to build this thing called the Event Horizon Telescope that I'm a member of. It's a collaboration of about 350 people. This is just part of them from our, of course, online collaboration meeting. And we just actually are having our collaboration meeting this week as well. And you can ask me more about it, but the basic idea is that we, instead of building a planet-sized telescope, which would be really expensive, we took existing facilities and we creatively linked them together so that they basically spanned the diameter of the Earth. And that gave us a baseline large enough to see something really tiny. And that tiny means we could see things that are about 25 microarcseconds in size. And that may not mean much to you, but that means it's sort of like if this telescope, if we turned it to, I'm here in Amsterdam, for instance, if we were sitting in New York, we could turn this telescope to me and you could read the newspaper that I was reading, or you could look at an apple on the moon. It's extremely tiny. The black hole we looked at was not tiny. It was about the size of our solar system, but because it's really far away, it was tiny on the sky. And that was what we needed to be able to start to see this event horizon. Now, I'm not going to go into details of the modeling, but I wanted to explain to you a bit more about what I mean by saying that one frequency of light only picks out one part of the system and that we need it all to really understand it. So when we want to model data from these black holes with the jets, we use supercomputer simulations, and I'm just shamelessly pumping some of the work of my group. But this is a simulation where we have a black hole in a box. We basically have all the general relativistic space-time effects. We wrap it. This is a slice you're looking at with a donut of stuff around it. We let it run, and we basically see, the sort of turbulence start up and these jets get launched, and then we're zooming out very quickly, and we can manage to reproduce these kinds of outflows out to millions of times the size of the black hole. So we're starting to probe really what happens, but how do we test these ideas? We need to make light from them and then test it against what we get from telescopes. And so this is what's called a volume rendering. So it's basically like we've just sort of shining a light on the outside of the structures in the simulation. So here you see the disk, which is wrapping around and something's starting to fall into the black hole. And then in red are the jets being ejected. And now when we make the light that the Event Horizon Telescope would see, we don't see all of this, because what we've done is we've picked one particular frequency in the submillimeter at 230 gigahertz, if that means anything to you. And then because we've made the telescope so big, we've picked out a tiny size scale. So we're really just looking at the light in one frequency coming out from just outside the black hole. And you could see the event horizon is being traced by this sort of ring here, more or less. And so we can try to learn about space-time effects. But if we want to connect everything we're seeing here to these larger jet structures, then it becomes a little bit more complicated, because we don't have that information. So we knew going in that this was going to be the case. And so what we did was, at the same time that we were looking with the Event Horizon Telescope, we also looked with many other facilities. Because now this is, again, looking in several wavelengths. This is, again, a Hubble image in the optical of the same M87 system with the black hole in the center. This is a galaxy. It has this big jet. And this jet is also bright in all of these different wavelengths. And so we're using both ground-based radio, space-based telescopes in the X-ray and Hubble to look at this and to understand, what exactly is coming out of this black hole and how can we understand it better. And so, in fact, we had a really large amount of telescopes. This is showing you the campaign in 2017, where we had, this is our days, but then the Event Horizon Telescope was looking just around 1 week. And then we have all of these different facilities from radio all the way up to the gamma rays looking at this at the same time. And then we can try to start to piece together some of the physics of this. And this is the beauty shot, just showing you all of the different scales from the black hole itself, zooming outwards to start seeing the jet in the radio bands. And then here's in the optical UV with Hubble, we can start to see in the X-ray. And you can note that different facilities are able to pick out different things. Some are looking at small sizes, some are looking at larger sizes, some are fuzzy, they don't have as good resolution, some have very good resolution. And if you look at this, particularly in the gamma rays, the whole galaxy is basically just a dot, because they don't have very good spatial resolution. And this is where I start moving towards the discussion of particles, because there's a lot of questions we have about the gamma rays together with particle events, and trying to figure out where these things are coming from is really important on the sky. But of course, if these are just basically dots on the sky and we can't really see inside the objects, it's very difficult. So now I'm going to start talking a little bit about cosmic rays and neutrinos, which are another signal from these extreme objects. And basically, you know, we have detected these cosmic sources or these cosmic particles since the early 1900s on Earth. And there's been a big debate about where they came from. They can't seem to come from Earth. And in fact, we can't even reproduce them with our best labs. So this is the LHC and CERN, basically have this big, huge track with a strong magnetic field, and you can whip protons up to very high energy. And this unit probably doesn't mean much to you, TeVs or tera electron volts, but it's equivalent of having a single proton that gets ramped up to energies where it has kinetic energies like a whole mosquito, which is made of many, many protons moving at 3 kilometers an hour. Okay, it doesn't sound that impressive, maybe, but it is pretty impressive. However, compared to outer space, it's not. The things that we find on Earth that we think are coming from outer space end up having maybe millions, tens of millions of times more energy coming out. And so we think the only things that have tracks and magnetic fields big enough are these huge jets in space. And these are accelerating these particles. But there's really been no exact smoking gun at the moment. It's just a theory. And there's also debates about what could be doing this. Could it be happening right outside the black hole or happening further out in the jets? And so we're trying to basically test between different theories. But if everything is basically inside the sort of resolution of the telescope, we can't pick apart the different pieces. And so one of the key points of this is that, first of all, if we see some particle coming to Earth, we'd like to be able to maybe trace it back to the source and say, aha, you know, it's coming from this black hole. But it turns out to be very difficult for other reasons, because cosmic rays, these charged particles, get deflected by the magnetic fields. And so they don't point back to their source. There are other particles created when the cosmic rays interact in the source, and they make neutrinos and gamma rays. Neutrinos are particles. Gamma rays are photons or light, but they basically are so high energy, they start to act like particles. Neutrinos are hard to detect, so we're starting to be able to detect them now. I'll say something about that in a second, but they basically also just pass through the Earth and pass through our detectors, so it's hard to get enough of them to really add up enough events to trace it back reliably. And so gamma rays turn out to be one of our best hopes because they're a tracer of these other particles. And so this idea of multi-messenger means that we start to combine all these different facilities that look at the light, but also look at the particles. And the Cherenkov telescope array, our hosts for the webinar, is the next generation gamma ray facility. And I'll say a little bit more about that, but this is really a phenomenal experiment that will be going online in something like the next 5 years and is going to revolutionize this field quite a lot. So starting already a few years ago, there was already the first coincidence between a single neutrino event and then, you know, again, people said, okay, how do we trace this back on the sky? This is from the IceCube collaboration. And they could make a sort of circle on the sky and say, wherever this neutrino came from, it came from this area. And the problem is this area is so big on the sky that you could have, you know, a ton of stuff in there. It's very hard to really know what would actually be the source. This is about the size of the moon or more on the sky. And if you think about all the stuff that's behind that, you know, what could be contained going all the way out into the universe, it's a lot. So what you do is you look for coincidences with something doing something interesting in the gamma rays at the same time. And they found that there was a supermassive black hole that was flaring in the gamma rays. But because the spatial resolution of these the current generation of telescopes are not that great, you know, it's still a little bit of a statistics game. Are we sure that these are correlated or not? But it's a very promising thing. And in the future, we're going to have bigger facilities and be able to actually know in more certainty if these things are correlated. So here's part of the thousands of people in the Cherenkov telescope array collaboration. And I won't say too much about this because I think this has been covered in other talks, but it's being built both in the North and the South Hemisphere, coming online fairly soon. And by putting together hundreds of telescopes of different sizes, we're able to actually become much more sensitive, about 10 times more sensitive than the current facilities, which are also pretty amazing, but especially better with the source localization and also orders of magnitude better for detecting things that flare very fast. And if flaring is something we're looking for to correlate it with other particle events, then that's a really important thing to have. And so, for instance, just taking as example, M87 again, this is a radio image of the inner part of the galaxy. So the jets that I was showing you before are basically buried inside here. And you can see that the current generation facilities, to them, everything is basically inside this error circle and they cannot see any structures. But CTA will already be able to pick out the area around the jets. And that doesn't seem so good, but there's another quality, which is besides being able to say your source is inside this box, it's also about trying to figure out kind of the location of what's called the center of that box. And you can actually tell the difference between different areas. So when you zoom into the inner parts of the jets, as we've been looking at, the bottom of this is the black hole, the current facilities have the ability to tell the difference between segments that are about that big on this jet. So they could tell the difference between this part of the jet and this part of the jet. But the big debate at the moment is really between sort of two parts of the jet near the black hole and this inner part that's all within that error pointing. And so CTA will actually be much better and be able to see, for instance, if there's flaring that changes on one part of the jet or the other and help discern between these different types of models. Now, I just want to say a bit more about the time aspect, and I'm almost finished, and I'll say a few things about gravitational waves. Now, it's important to know that the sky is dynamic with extreme objects. So this is a view, just a movie of the X-ray sky flickering in the X-rays over many months, all these different sources. You see the same thing in the radio. These are pulsars, X-ray binaries, neutron stars, black holes that are just going on and off. And we want to be able to identify these as particle accelerators using the gamma rays, but we need to have good resolution and we need to be able to detect them. And I won't go into the details of this plot, just saying this is something measuring something about how sensitive instruments are. And then this is telling you how fast the object would be flickering. And the best telescope we have now to sort of look for these transient events of the gamma rays is called Fermi. But because it's just a much better telescope being built all over, having much more collecting area, the Cherenkov telescope array is going to be about 10,000 times better at finding these flickering sources on very short timescales of minutes to hours. And so that's a big revolution in our field, and it's going to help us actually characterize these sources and help us put together where the particle accelerators are. And so I'm almost done, but of course we have to talk about gravitational waves. And so there's a new class of source that we have just found in the last few years, which is colliding neutron stars that are in a binary system. So this is the end stage of stellar evolution. And the first pair, and so far the only one found so far, of these merging neutron stars turn into the ultimate multi-messenger event, because we had this sort of crash where these two come together and they gave off a big burst of gravitational waves. And they're basically just shaking space-time, and then they come together and they form a black hole. This, I'll talk about that in a second. There's a kilonova, so you get this big nuclear explosion where heavy elements like gold and platinum are formed. We start to see optical and UV light. The black hole is formed and launches jets, just like we saw in the supermassive black hole. We get particle acceleration, and we expect that we'll get cosmic rays, neutrinos, gamma rays, and the rest of the light. Well, we did see the gamma rays. In fact, we saw them first, and then the rest of the light followed. But so far, it's so difficult to detect cosmic rays and neutrinos that there wasn't a clear association, but that's what's going to be coming in the future. And then, we have the first neutrinos detected from these supermassive black holes, and we're starting to understand the drivers of these entire systems. So you can imagine in the next decades, as these facilities get better and better, we'll be able to develop a much fuller picture of all of these phenomena. Okay, I'm going to skip over this slide, but just to say that localization becomes a real challenge. And so by combining facilities, by combining facilities, you can actually start to see many different things that you couldn't measure from one alone. And so, for instance, the other big advance is going to be the Event Horizon Telescope that I mentioned, expanding into a larger facility at around the same time that the Cherenkov telescope array is going to be in full operations, plus all of the multi-wavelength and multi-messenger. In this case, the gravitational wave monitoring will also happen for small sources, and we'll have monitoring for many, many supermassive black holes. And we're already looking at these with the Event Horizon Telescope with many facilities, but the future is going to be big and small, combining information from across the spectrum, particles, and gravitational waves. So if you look at a map of the coming decades, you could see these facilities from gravitational waves. They're coming online. CTA is going to be starting somewhere around here. You have neutrino detectors, the next generations. cosmic rays, and then everything from the radio all the way up to the X-ray. And so we plan, and we're learning as we've been doing this, we've been learning how to do this more efficiently, how to talk to each other, how to collaborate, and how to arrange these types of campaigns. So it's basically the end of my talk. I'll just summarize that extreme objects mean a very specific thing that you might not have thought about, which means they're very different than the stars that most of humanity has known. So you're living in a special time that you can learn more about the universe than the last, 100,000 years of human existence, or however far back it goes. You have strong gravity and matter under the most intense possible conditions that we're starting to understand about this interaction. By combining multi-wavelength and multi-messenger, we really need to do this to identify sources and find out where they are in the sky, spatial coincidence, and also to understand their physical properties. And we're especially, of course, at CTAO, we're biased, but we're very interested in very high energy gamma rays, because these are the optimal tracers of particle acceleration. So even though cosmic rays and neutrinos are coming out, they're harder to detect. So we like to look at them in the gamma rays. And with the dream team, combining all of this with the Event Horizon Telescope, especially as it goes in the future, we're going to be able to see, hopefully, during gamma ray flares or neutrino events, actual structural changes in the source, maybe near the black hole or in the jets, that we could start to identify exactly what's going on to accelerate these particles. So with that, I'm finished. And Alba, I guess you are moderating the questions. I hope some of you have questions for me.
Thanks a lot, Sera, for this super nice presentation. Yes, there are already some questions. So just a reminder to everybody, if you have questions for Sera, you can leave them in the CTAO Facebook or YouTube channel, and she will answer them now. So let's start with the first one from YouTube. Gaurav says, how can multi-messenger astronomy can help us better understand the nature of dark energy, constitution of dark matter, and antimatter symmetry in our universe?
Yeah, that's a long, deep question. It's a good one. So in fact, I've been focusing on the astrophysical types of sources, but of course, like we already know that multi-messenger or even multi-wavelength astronomy has helped us understand the nature of dark matter, right? I mean, maybe you've been familiar with this, but they were able to trace the matter by looking at this hot gas, like I said, with the X-ray, compared to using other methods to trace where the dark matter was using gravitational lensing. So that's another way of combining gravity information and light information. And they found out that when these two clusters of galaxies collided, basically the normal matter sort of stuck together and the dark matter continued going through. And so that told us already that dark matter most likely has at least a large part of particulate type of background. Now, for things like dark energy, we actually use a lot of astronomical facilities to trace the distribution of galaxies in the universe, for instance. And then that's one way that we measure how much energy is in the universe, and we constrain the dark energy contribution. Now, it's interesting because, in fact, the distribution of galaxies can also be affected by black holes. And that's something we don't have that's modeled very well. So some of the things that I'm talking about will feed into this whole modeling scheme to actually pull out the effects of dark energy. Now, in terms of antimatter and matter asymmetry, I'm probably not the best person to ask on that. So that one I can't answer so well, but I think the other two I touched on a bit, and these are very deep questions, yes.
So thanks a lot. I think it's perfectly answered. I don't see now further questions. So in the meantime, let me ask you myself one question. You've been talking about this super big international collaboration, observations with different instruments, observatories, and so on. But how can one organize an observation on a source in a worldwide level?
Yeah, this is, in fact, it's a really difficult thing to do, because people don't quite realize this, that first of all, the Event Horizon Telescope, it's not ours. We're basically borrowing the telescopes of other people. And so we have to, as the collaboration, propose also for the time. We're given a window of basically 10 to 12 days in which we're allowed to use the telescope in this mode where the telescopes, where we string them all together into what we call a phased array. And then we can observe, and we have to take the data all during that time. But then the point is, we have a certain amount of sources that we're looking at. And then we're trying to arrange, for instance, this multi-wavelength collaboration around it. So we also have to propose, because each one of those, whether they're on the ground or space, are usually very competitive facilities owned by, NASA or ESO or ESA, and there are committees that judge the proposals. So it's just like asking for money. Basically, astronomical data is the currency of the field in some sense, and the oversubscription rate's very high. And just because, it might sound cool to say, hey, yeah, we're looking at a supermassive black hole with the Event Horizon Telescope, doesn't guarantee that we get the time. So we have to write the proposals, we have to argue for this. Then once we get even the time on these facilities, it's not clear that they can all line up their schedules at the same time to look simultaneously, because some of them, for instance, are in space and they need to point their solar panels at certain times to the sun to get energy, or there's thermal constraints, because if they point at the wrong part of the sky, they might burn their optics out, and so we have to go through this whole, what one of the guys in the collaboration calls it the Sudoku of scheduling. And every night we go through this stressful triggering during the campaign where we say, okay, we think we're going to observe tonight. We think we're going to observe this particular source. We all sit in a room and we look at all the weather across the facilities on the ground. We talk to the people with the space telescopes, and then we make a go, no go decision every night. And and so the fact that we managed to do this so well for M87 in 2017 was really, it came out really well. And we're doing it now. We did it for also the black hole Sagittarius A star, which is our second horizon target, where we can see an event horizon as well. And that will be published quite soon. We're working very hard on this. But we've got data from many other sources in many other years, and we're continuing to do this. So it's really, I think, for those people who are not familiar, it's really an enormous amount of work from huge teams of people and international collaborations.
Well, I have to say, it sounds difficult, but also exciting.
Yeah, and it's fun to work with so many people, and you really get to know a lot of people. And I think, science is cross-border, right? And that's an important point to make, that despite maybe, one country not talking to another for some reason, we still talk because of science. So
that's nice. Okay, so I don't see any further questions. So let me maybe finish the webinar with one based on your experience. And so what do you think it would be the most exciting discovery or the physics that you are really looking forward to with this new generation of observatories, with the sensitivity, with an unprecedented sensitivity and so on?
Yeah, I mean, so I'm really interested in the way that that particles get accelerated. That's kind of the meaning of the field astroparticle physics. So how do these astrophysical sources manage to not only launch these jets, but somehow these big jets trickle down their energy down to the particle level? And this is something like 20 orders of magnitude in scale. And we're really far from being able to understand this. So for me, I sort of hinted at it in the talk, but when we start to have the next generation Event Horizon Telescope, which is going to be able to really see much deeper and better into these sources and connect, we'll be able to see both the ring, the sort of donut of the black hole, and connected to the base of the jets in real time. And we'll be co-monitoring with CTAO, of course, and with neutrino experiments. And that moment when we know that there's a neutrino flare, that something was accelerating a cosmic ray, and we can actually catch that maybe something's moving, like a shock or something in the system that tells us what it is and gives us a big clue about that. I think that would be really exciting, because also it would give us answers that we would be able to use for the other types of sources, like gravitational wave event sources, where we can't see in that amount of detail. So there's a lot of physics we're still kind of missing. And if we could fill in the gaps this way, then we'll fill in the gaps for a lot of sources.
So it's an exciting future that we have ahead of us. Okay, so I would say let's stop here. I would like to thank you again, Sera, for this wonderful presentation and for the answers to all our questions. And I would like to thank also the participants, the viewers that join us today, and also through all the series. Thanks a lot. As I said at the beginning, I hope you really enjoy the series. And if you miss it, if you miss any episode, remember that you can watch it on our YouTube channel. And with that, thanks a lot. And
Thank
see you in the
you.
next event.
Bye.
Ciao, ciao.